binomials. So what's a binomial? Simply an expression that contains two terms. Bi meaning two, nomial meaning terms. Right, so we start with the simplest binomial of them all. 1 plus x to the power of 0, which is of course 1. And then we can make it to the power of 1 and we get 1 plus 1x. And then 1 plus x squared ends up being 1 plus 2x plus 1x squared. And then cube, well, I can multiply that by 1 plus x, and we get 1 plus 3x squared plus x cubed. And then we go to 1 plus x to the power of 4. We could multiply that by 1 plus x, and we come up with 1, 4x, 6x squared, 4x cubed plus x to the 4. And of course you could keep going, but a pattern is emerging. Now, Blaise Pascal gets all the credit for this, by the overrated. Spotted that pattern, and we now call it Pascal's triangle. There's 1, 1, 1. Then the next line 1, 2, 1, and we keep going. And by placing it in that triangle formation, hopefully the pattern emerges nicely. And we note symmetry, and then we keep going. See 7. That's not a bad row. And we keep going. There's the 8th one. And then we can keep going. And then we get to my personal favourite row. I'm sure you have your own, but my personal favourite is this one. Look at that. That's just sensational. Oh, no. Come on. Look. There's symmetry, but you get to the middle, 2, 5, 2, symmetric. But then, look. 1, 2, 0, 2, 1, 0. Same numbers rearranged. There's just so much happening in that row. That's a great row, the 10th row. So you get to the 11th row. It's okay. There's 12. We can keep going on and on and on. But I think I stopped there, didn't I? At 12. So if we now have to expand out 1 plus 2x on 3 to the power of 7, voila!
Oh, that's my favourite.
It is. 7, your favourite. So we've got to remember to write those binomial coefficients, as we call them. And then the powers of 1, the first term, start at 7, go down by 1. The powers of 2x on 3 start at 0 and go up by 1. So at any point, you can look at any term, and the two powers add up to give, in this case, 7. Well, let's tidy that up. And voila, there's the expansion. Now, where is it really handy for something like this? See, imagine you're out shopping, and someone comes up to you, as happens, and they say, "Excuse me, can you tell me what 0.998 to the power of 10 is?" It's okay, I only want to know to 8 decimal places. You've left your calculator at home. Oh, jeez. But then you remember, hang on a sec. 1 minus x to the power of 10, because 10 being the great row that it is, you'd remember that one. And I could expand out 1 minus x to the power of 10. Now it's minus, not plus, so we've got to remember to alternate each of those terms. And then you go, well, hang on, but 0.998, I could write that as 1 minus 0.002. So if I substitute in x is 0.002, then I can work it out. But they only want it to 8 decimal places, so I can stop at the power of 3. Because after that, to 8 decimal places, every one of those would be 0. So you can avoid total embarrassment and now go, oh, well, I can work that out. And there it is. Put 980179004. Yes. Maths in the real world. Yeah. So we have to find the coefficient of x squared in all this expansion. So the second one we could expand out, but I tell you what, I don't really want to expand that whole thing out, so I'm not going to, because I'm only interested in the x squareds. So the 2 must be times the term 6 times 4 squared times 5x squared, and the minus 3x must be times the 4 times 4 cubed 5x. I didn't need to worry about all those other terms. So the coefficient, so notice I haven't put x squared there, because they're only interested in the coefficient, turns out to be 960. So 15a will have a play. Oh, that rhymes.